Hi, this is Joe and welcome back to the shop. In this video we're going to start wiring up the DC variable speed motor controller. What we have is we have a multimeter, a DC multimeter. We have a DC variable speed controller that works on pulse width modulation. I'll explain what pulse width modulation is a bit later. So let's get started. We'll try to get this all wired up and assembled and then show you how we use it to test motors. I'll put all the parts that I purchased, most of them are from Amazon. I bought the plastic electrical box from the local big box store. First of all, we have some 100 amp terminal lugs that we're going to put two on the left side for the input, two on the right side for the output. The output will go directly to the motor. We have to wire up both the speed controller and the DC multimeter inside the box. So first off, we're going to mount the lugs for input and output for the voltage. So let's get going. We use two nuts to mount the lugs to the case, and then there's two more nuts to hold. In this case we're going to wire up some terminal lugs, or what I like to call terminal rings, and that way we don't have to solder those. They'll be semi-permanent. So that's what we're going to do there. So we have the input side wired. Now we're going to wire in the output side. The output terminal lugs are mounted. Now we're going to take some 18 gauge wire, and we're going to use the 18 gauge wire to wire in the DC multimeter. There's 4 terminals on the back. On the back of the display there's a wiring diagram, also known as a schematic. I also have some instructions, and what I'll do is I will shoot some images of this and put it at the end of the video so you can see what it looks like. Mostly it has a more detailed description of the actual wiring of the display. The variable speed controller is rated at 40 amps and has 2 inputs and 2 outputs. The multimeter has a 100 amp shunt, so I'll be wiring the most of the load and input using 14 gauge wire, which will give me 32 amps max. Oh, just keep an eye and make sure I don't go over 32 amps. Again, the speed controller is rated to 40 amps. This is 100 amp shunt. So again, we'll be using 32 amps max using 14 gauge wire. We've crimped on some terminal connectors, or what I call ring connectors, on the wires that are going to the multimeter display. And if you look, the red and the blue have larger connectors because one lead is going to go to the input lugs. The other lug is going to go to the large bolt on the shunt. So when I assemble this, I'll show you what I mean by that. The green wire goes to the right hand side of the shunt on the small bolt. The yellow wire is going to go on the small bolt on the left hand side of the shunt. I'm moving the ring terminals to the inside to give me a little bit more room on the bottom of the case. I don't want to pinch these wires. The blue wire goes to the large bolt on the left hand side of the shunt, and also the black or negative side of the input terminal is also going to go here as well. So I'm going to do some splicing now of some 14 gauge wire to go from the input black or negative side to the negative side of the shunt. We now have the 14 gauge wire with the ring terminals crimped on. Again, this is going from the negative side of the input to the negative side of the shunt. So we'll put this off to the side. We're going to make up all the remainder of the wires for the box, and that way we can wire and tighten everything at one point. Now let's take the positive side from the input terminals and go to VIN positive. So we have input positive and negative. We have output to the motor positive and negative. Now let's wire in the connectors to the shunt. What I'll do is I'll mount the shunt onto the bolts, and then we'll put the wiring onto the lugs, and then we'll tighten the nuts onto the bolts. What we have now is we have one of the input negative going to the left-hand side of the shunt. Then we have the display negative that will go to the display. Then we have the yellow, and we have the green. These two leads will also go to the multimeter display. I have everything wired now. I'm going to run the wires through the cover, and then we will wire in both the display and the speed controller. What I'll do at the end of the video is I'm going to put a very descriptive wiring diagram, so if you want to build one of these at home, it'll be a little bit easier to see where all the wiring goes. So let's go ahead, get the displays wired in. What I'm going to do is I'm going to test everything, and after everything is working, then I'll take the speed controller and the display and I will hot glue them to the cover. But until we get everything working, I'm not going to do that. So let's go ahead and wire everything up, and we'll do a test. We've used a little spray adhesive to attach the foam gasket to the back of the cover. I don't anticipate any moisture or water getting into this unit, as this will be used indoors. But just to keep the dirt and the crud out of there, I've used some spray adhesive and put that on there. We have the cables routed through the cover. We have your VN negative, your VN positive. We have your motor negative and your motor positive. Then on the display, we have the red, which is going to the input positive. We have the blue, which is going to the left-hand side of the shunt. I'm going to have to change the wiring design a little bit. What I attempted to do with the multimeter display was put the display downstream of the speed controller. That way my voltage reading would reflect the percentage of what the speed controller was delivering to the motor. But the display did not like the pulses from the pulse width modulation on the speed control. I'll explain what pulse width modulation is here in a bit. But anyway, now I'm going to have to take and put the display upstream, or basically on the input side. And then what I did was purchase just a separate voltmeter that I can then mount on the downstream side, so that I can then view what the voltage reading is at the various percentages from 0 to 100%. So let's go ahead and wire that in. Again, don't worry, at the end of the video I'm going to post some images of how I properly wired the motor controller. I have everything working now. Let's go through the operation. Off to the left of the controller, I have a 12 volt power supply. The motor over here is a 24 volt motor, so we'll run that at a considerably less voltage, but this will work just the same. Up top here on the top I have the speed controller. There's a menu button, and there's a forward and reverse. you have your increased speed, decreased speed, and you have a run stop. So that is run, that is stop. So we'll turn it on to run. Below we have a multimeter gauge that measures volts, current in milliamps and amps, power in watts, and energy in watt hours. We'll run this motor for a little bit and then I'll zoom in and let you get a close-up of what the displays look like. So let's go ahead. You can watch. I put a piece of tape on the motor here, and on the speed controller there's basically two different ways to control the speed on a DC motor. One is by varying the voltage using a voltage controller. The other, which this is using pulse width modulation, and I'll explain that here in a minute. The speed controller that uses pulse width modulation is more efficient. Let's go ahead and get the light on so you can see here. So if I start increasing, notice the voltage up at the top when not running the motor. We're pretty much running the same voltage, 13.91, 13.9. So with no voltage or very little current going through the motor, the display up here is reading the same as the input voltage. As we start to add power or speed to the motor, this display will start going down, indicating that there's more voltage being directed and current being directed to the motor. So let's go ahead and start increasing. Notice we start getting up 9% and the motor starts to turn. The current now is 0.07 amps. We have a 0.9 on the power, and on the energy it's not reading at all because it's not high enough. So let's go ahead and go up some more here. As you notice, as I increase the speed, the percentage goes up. The current is starting to go up. The power is starting to go up. And notice the voltage at the top is decreasing. So that means we're directing more of the input voltage through the speed controller to the motor. So let's take this up a bit more. So now 50%, we have 0.4 amps or 40 milliamps. We have 55 or 56 watts. We still don't have energy on there. So notice the voltage at the top. It's 6.7 volts. So at 50% duty cycle, we're pretty much consuming half of our input voltage. So as we go up some more, notice the motor speeds up. The voltage is decreasing. That's going to the output, which is the motor. Okay, let's go take it up here a bit more. Let's take it up to 75%. Okay, we have current is a little bit less, so 13.87, which is normal, where the motor is creating a load, so the power supply is going to decrease a little bit. Current is 0.62 amps or 63 milliamps. Power is 8.7 watts. The motor is spinning at 75% of its capacity. Notice the output voltage is down to 3.1, or what's the remainder. It's pretty much that is all the remainder of that voltage is being directed to the motor. So this is in excess of our 13.87 volts. Okay, so what is pulse width modulation? Let's talk about that. That is currently that is the most efficient way to vary the speed of a motor, a DC motor. So what is pulse width modulation? So let's do some visualizing here. Go to a light switch, any light switch in your house, and let's visualize that to that light switch you have a DC motor connected to that light switch. And for the sake of visualization purposes and being able to calculate adding and subtracting here, let's say that you can turn that light switch on and off 100 times a second. Okay, now don't do this with your significant other or spouse around. If they see you flipping the light switch very, very fast, they'll think that you've been quarantined a bit too long with COVID, and they'll probably send you to the funny farm. So again, if you're going to do this by yourself. So let's talk about this. So if we can turn that light switch on and off 100 times a second, and the amount of time that the light switch is on and off is exactly the same, that means that your duty cycle is 50%. So the light switch is on 50% of the time, and the light switch is off 50% of the time. Okay, so the controller in this speed controller is turning on and off the motor very fast. So again, we're using 100 times a second because it's easy to do the math. So if we turn the switch completely off, the motor's not going to run. That means our duty cycle is 0. Likewise, if we turn the light switch on and leave it on, the duty cycle is 100%. The motor's going to be spinning fast as it can. So last little example here. So if we flip that light switch 75 times a second and it's off 25 times a second, that means we're getting 3/4 of the total RPM to the motor, so our duty cycle is 75%. So all a speed controller does that uses pulse width modulation is it very rapidly varies the duty cycle by switching the motor on and off very quickly. So let me reposition the camera now really close to the display, and I'll take the motor up and down, and then you can watch the various display readings on the speed controller and on the multimeter. I have the camera really close now so you can see both displays. Let's go ahead and increase the speed and watch. You'll see the percentage on the top, and you'll see the multimeter display on the bottom. So as the motor starts to turn, notice the power and the current. So we're 26%, 0.20 amps or 20 milliamps, 2.7 watts. Let's take this up some more. We're 50% duty cycle, or basically we're turning the light switch on and off an equal amount of times per second. Notice we're 40 milliamps, 5.6 watts. Okay, let's go up some more. What I'll eventually do is put an RPM sensor on the motor so we can then determine what the actual RPM is. But right now this is going to be good enough. Basically what I'm concerned about is can the motor be successfully speed controlled, and what the current is at various RPMs. Now this is in a no load situation, so as you apply load to a motor, what's going to happen is load is directly proportional to your current. So the more load you have on the motor's going to consume more current. So let's take this up. But again, we're freewheeling the motor here, so there's no load whatsoever on the motor. Let's take it up 75%. Notice we're 75%. We're 8.5 watts and 62 milliamps. Let's take it all the way up to 100% here. I don't know if you can hear, the motor is whining a little bit, but it is a pretty quiet motor. Okay, we're 100%. Notice you can't see the top display, but the top display reading voltage at the motor is 0. So that means all of the voltage is being directed to the motor. Notice 13.85. So that means there's a little bit of voltage sag because the motor is consuming some power. So notice here we have 85 milliamps, we have 11.7 watts, and we have 1 watt hour of energy. So let's take it back down. So as you can see, this is a pretty nice little configuration. This cost me at the local big box store $15 for the box, around $15 to $20 for the speed controller, and $15 and change for the display. So right around $50 I was able to put this together. I want to use this when I get various motors. I usually buy all my motors used off of eBay or Craigslist or OfferUp, and that way I can then take and run the motor through some paces. Eventually what I want to do is try to put together a little dyno, an eddy current dyno, which then allows me to put a load on the motor, and then I'll be able to measure horsepower. But I'm more interested in various loading of current on a given motor. So let's say if I want to make a scooter and I want to make sure I have a proper controller, and I want to determine the discharge rate of the battery that I'm using. I want to make sure that that current load is proper for the motor, match it to the battery, and make sure that all my wiring and everything is a proper gauge, so that I'm not as I put the motor under load, I'm not going to blow past any of the specifications, because the wiring is too thin, you'll fry your wire. If you're consuming too much amperage, you may burn out your controller, and you want to make sure your discharge rate on your battery is enough so that the motor will properly run without overstressing or overloading your battery, which could damage your batteries. So hope you enjoyed this video. We'll do some more with this. I may put together a little eddy current dyno in the future, but any questions, put them down in the description or in the comments section, and we'll see you next time.